All right, so this is a continuation of the section 5.3 notes. In class, we got through everything except for the net change theorem, so we'll go through that right now in this video. To start off, let's just look at something kind of straightforward here. If we have time going along this axis and velocity going along this axis, and let's say we have just a constant function, and we'll say that that's 60. And time-wise, we'll say we're doing, let's put 2 here, 1 here, and these will be in hours. Okay, so this is 1 hour, 2 hours. And basically what this function is telling us is that we have, again, the velocity function is always 60 miles per hour. And assuming that the vertical axis is measured in miles per hour. And so we have this nice constant function. My guess is you can immediately tell me how far this object has traveled in 2 hours, right? All we have to do is multiply 60 miles an hour times 2 hours, and we get a distance traveled of 120 miles, right? Not a surprise. 1 hour goes by, you go 60 miles. Another hour goes by, you do another 60 miles. But if you notice, that's really just the area under our velocity curve, right? If this is our velocity curve, the distance traveled is going to be the area under that curve. Okay, that's kind of nice. So with that in mind, let's take a look at this example that's already all worked out here. But we're just going to kind of hold on to this idea that if we were to integrate the velocity function dt from the beginning point in time to the finishing point in time, in other words, from 0 to 2 of 60 dt, we can use the fundamental theorem of calculus to take the antiderivative that gives us 60t, and we're evaluating it from 0 to 2, and we get 120 minus 0. Okay, so that integrating the velocity function gives us the distance traveled. Now, looking at this example here that, again, is all worked out for us, but suppose a car is moving due north, we're calling that the positive direction, at 40 miles per hour between the hours of 2 p.m. and 4 p.m. Then the car moves south at 30 miles per hour. So if north is the positive direction, we're assuming south is the negative direction. At 30 miles per hour between 4 p.m. and 5 p.m. The graph shows speed versus time for the given motion of a car. I'm not thrilled with that wording. I'd rather call this velocity. So we've got our velocity function, which is here between the hours of 2 p.m. and 4 p.m. And then our velocity function jumps down here between 4 p.m. and 5 p.m. Okay, now, if you think about what happened, the car drove north for 2 hours and then stopped and then went back south for an hour, right? So first it went up this way, then it came back down that way. All right, well, here it's explained that we can use the definite integral to calculate the net displacement, okay? Now, what do we mean by net displacement? Again, let me go back to this little figure here. The car traveled north for 2 hours. Then it turned around and it traveled south for 1 hour at a different speed, right? So it started right here and it traveled all the way up there and down a little bit, but its net displacement is where it ended up, right? It ended up here. So this is the net displacement. Even though it went beyond that point and came back, the net displacement is just where it ended up, okay? So what they're saying is if we go ahead and integrate, the velocity function between the hours of 2 and 5, we should get just the net displacement. Well, clearly, if we're going to integrate this, we've got to do it in 2 pieces, right? So this first piece, we've got the velocity function up top here, which is, I'll call it v sub 1 of t, even though they don't use that notation here, but that's equal to 40. And here v sub 2 of t is going to be negative 30. And again, it's negative because it's going south between the hours of 4 and 5. So if together these two velocity functions make v of t, we have to integrate these guys separately, okay? And so when we integrate these, and you can check the integration on your own, but basically this first one becomes 80. That means that the car traveled 80 miles going in the north direction, then it stopped, and it traveled 30 miles in the south direction. And so we subtract those in order to get the displacement, which is this distance here that basically where it ends up with respect to where it started. Okay, so that's what displacement is all about, right? Displacement here is simply integrating our velocity function, and it ends up taking positive and negative velocities into account. So we end up just with where the car ends up at the end of this back and forth. Okay. Now, that's not the same as the total distance traveled, right? We want now to look at total distance traveled, right? I think what we have is from here to here, the car traveled 80 miles, right? That's the area right there, 80 miles. And then after that, it traveled an additional 30 miles, and that's this area down here. Okay. Now, so what we want to do there is we want to take our 80 plus our 30, and we should end up with 110. But the problem with that, as we've discussed in class, this region here would have a negative result if we integrated it because it's below the t-axis. So what we're going to do is instead of integrating just plain v of t as we did with displacement, net displacement, we're going to integrate the absolute value of v of t for total distance traveled, okay? And when we do that, we're going to take our v2 that we have right here, and we're just going to make it positive. And that's what you're seeing right there. And then if we integrate these, we end up with a result of 110, which is the 80 miles going north, and then adding on the 30 miles going south, okay? So displacement, the idea is we're going to integrate the velocity function as is, and total distance traveled, we have to integrate the velocity function in absolute values because we're not taking into account where the object is going in the positive or negative direction. Now, with that in mind, we have the net change theorem. And what you'll notice, if we just focus on this right here, it looks just like the fundamental theorem of calculus part 2, where capital F is an antiderivative of f prime. Okay, now I do have a little issue here with the notation. That symbol should not be there, so let's go ahead and get rid of it. One moment. So we're going to get rid of this symbol because that shouldn't be there. It should just be f prime. Okay, so the definite integral of the rate of change of a quantity, think of that as our velocity from the example above, gives the total change or net change in the quantity on the interval AB. So basically what we're saying is if you integrate the velocity function, then we're going to get the displacement that we saw above. Okay, so good news is this is just the fundamental theorem of calculus again. All right, so looking at what's next, now we're looking at S of t, right, for position, which is the antiderivative of v of t. So I've got to clean up my notation here as well. So we'll just go ahead and get rid of that and put a prime. So fix that in your notes, please. So this right here and this right here are saying the exact same thing. It's just here, instead of f prime, we have velocity, and instead of capital F, we have position, okay? So that's where that is. Now, what we saw in that previous example is the difference between displacement and total distance traveled. So displacement, we saw that we're going to integrate from A to B the velocity function, dt. And total distance traveled, we're integrating from a to b the absolute value of v of t dt, like that. Okay, so let's go ahead and look at an example where we're doing this. We already saw one, right? This one was nice and straightforward because all the velocity functions were, both velocity functions, I should say, were positive. But let's look at one that's maybe a little different, but kind of similar. So example 6, a particle moves along a line so that its velocity at time t is v of t equals t squared minus 2t minus 8, measured in meters per second. Find the displacement of the particle during the time period 1 less than or equal to t, less than or equal to 6. Find the distance traveled during this time. We're going to assume that these times here are in seconds. And also, I'm going to make one small change to this problem just for arithmetic reasons, because we want to make sure we have the concept down. I'm not worried too much about doing a whole lot of arithmetic. So I'm going to change this problem and change the 1 to a 0. Okay. And again, the only reason I'm doing that is so we're not spending a lot of time doing calculations. We're spending our time understanding what this concept is saying. So based on what we saw above, they want us to find both the displacement and the distance traveled. Let's go ahead and find displacement first. Displacement is the idea that the car goes driving north, then it turns around and goes south, and then it stops. Where does it end up? Not the total distance traveled. And from what we saw above, all we have to do here is integrate from a to b the velocity function dt with respect to time, that is. And so we're going from 0 to 6. We have t squared minus 2t minus 8 dt. So we integrate this. I believe we have an antiderivative of 1/3 t to the third minus t squared minus 8t, evaluated from 0 to 6. You can pause the video and double check that I did that correctly by taking a derivative. And then we're going to get 1/3 6 to the third minus 6 squared minus 8 times 6, minus plugging in 0 and everything gives us 0. And the calculation that I get from this is a negative 12. Now, this means that this vehicle started going in one direction for a certain amount of time, then turned around and ended up somewhere down here, right? That's why we have a negative displacement. And this is measured in meters. So we have meters. So we get negative 12 meters. It is, let's see, it just says it's moving along a straight line. So if it was a vertical line, it's 12 meters below where it started. That's all we're getting at there. All right. So now we've got to figure out total distance traveled. So even though I just erased what I had, basically we want to figure out this distance and we need to add on that distance to get our total distance traveled. So we'll do that next, as discussed above. So total distance traveled. That's where we're going to integrate from a to b the absolute value of v of t dt. All right. Well, in order to get that done, we need to figure out where our velocity function is positive and where it is negative. Okay. In other words, actually, let's do this. Let's start off by figuring out where v of t equals 0. Okay, so v of t, and I'll show you why we're doing this if you're not already seeing it. One moment. Okay, so we have t squared minus 2t minus 8 equals 0. That factors t minus 4t plus 2 equals 0. And then we get t equals negative 2 or 4. Time can't be negative, so we've got this 4 here. Okay. Now, we're going to check on either side of 4. Okay, I'm going to put 0 here, and I'm going to put 4 right there. And if we plug in, say, 1 into the velocity function, I think v of 1, let me move this. If I plug in 1 up here, I'm going to get 1 minus 2 minus 8. That's going to be negative, so that's less than 0, negative. And if I plug in 5, I'm going to get into v, right? V of 5 is going to be 5 squared minus 2 times 5 minus 8. That's greater than 0. So now I know where the velocity is negative and where it is positive, okay? And you're probably noticing the velocity function is a parabola. I'm not going to sketch this beautifully, but it's going to look something like this. If we put 4 right here, I think our y-intercept is a -8, maybe around there. Our parabola is doing, our velocity function, parabolic velocity function is doing something like this on the time from 0 to 6, let's say. And so what you'll notice is when we integrate here, we have all this quote unquote negative area, but when we integrate here, we're going to get positive area, right? And so what we found with the -12 was that we found that the net area when we integrate from 0 to 6 is -12, meaning there's more red area than green area. But now what we need to do in order to find the total distance traveled is we need to find the red area and make that a positive value because it's a distance traveled in the negative direction. We just want the distance. So the way we're going to do this is we're going to take our integral here and we're going to integrate from 0 to 4, right? That's the red region. And when we integrate from 0 to 4, we're going to take the negative of t squared minus 2t minus 8 dt. Basically, what that has the effect of is it takes this part of our curve and flips it up here. So we're going to get a positive result when we integrate. Okay. And then to that, we're going to add the integral from 4 to 6 of the original function t squared minus 2t minus 8. Okay, so hopefully that part's making sense. Again, this is the red area, but it's going to become positive. And this is the green area, which is already positive. Okay, so now it's just a matter of integrating this. So we're going to get, I'm going to go ahead and distribute that negative just so I don't make too many mistakes here. I've got a negative t squared plus 2t plus 8 dt plus the integral from 4 to 6 of t squared minus 2t minus 8 dt. And now we'll get an antiderivative or two antiderivatives. Okay, so at this point, you might want to pause the video for a moment and just double check that I did my antiderivatives correctly. We should always be checking our antiderivatives before we move on. I think it's in pretty good shape. So from there, we're going to plug in our 4. So we're going to get negative 1/3, 4 to the third, plus 4 squared plus 8 times 4. And then all of that, I'm going to have to subtract plugging in 0, which is just going to be 0 in this case. And then to that, we're going to add plugging in 6 to the second antiderivative. We have something like this. And I'm running out of space here, but now we've got to take that and subtract off plugging in 4. 4 to the third minus 4 squared minus 8 times 4. And it's going to be arithmetically annoying, right? There's a lot of math that needs to be done here, but the concept is there. We have the basic idea of what's happened. I'm going to go ahead and just tell you what I got. I got this result to be 124/3, which is approximately 41.3, and this was measured in meters. So the total distance traveled is going to be 41.3 meters. All right. So the main takeaway from this last little bit regarding the net change theorem is it's basically saying the same thing as the fundamental theorem of calculus. Um, Here we're applying it with respect to velocity and position. And to get the displacement, meaning where does the object end up after it travels along its path, is just integrating the velocity function. And to find the total distance traveled, we have to integrate the absolute value of the velocity function. And when that happens, we often have to split up our velocity function into the positive region and the negative region and integrate them separately and put a negative in front of the portion of the velocity function that had the negative region, right? We saw that right here, right? From here to here, put a negative in front of the negative 30 to turn it positive. And we also saw that right here, which was this guy, making it positive so that, or well, putting a negative in front of it to flip that part of the blue graph so it's positive, and we're getting a positive total distance traveled. So that finishes it off for that section.